Welcome everybody to the 11th and final online module for ManEc Fin 453 here in the finance program at the Marriott School housed at Brigham Young University. Today we're going to be talking about mapping the efficient frontier and the capital allocation line. So you can see we're now coming to the conclusion of our Excel modules for the semester, and we have a fairly tall order here in the final Excel module, which is to go ahead and map out the efficient frontier and the capital allocation line. Today we'll be dealing a little bit with the solver function, continuing with array and matrix functions, and I may even show you how to do a real simple macro to help you along. Goals for module number 11, as we've already said twice, we want to map the efficient frontier. You will do it for a portfolio comprised of 7 assets. I will be demonstrating with a portfolio comprised of only 4 assets. Once we map the efficient frontier, then we want to map out the capital allocation line. Now, just as a reminder, consider a chart in which the x-axis represents volatility or standard deviation, and the y-axis represents expected returns. On this particular graph, which is nothing more than a graph of return as a function of risk, investors prefer to be northwest on this graph. That would mean lowest risk and highest return. So investors have a preference to move towards the northwest on this graph. When you start combining assets into portfolios, you truly could wind up nearly anywhere on this graph. Well, I did it for a 3-asset portfolio. I'm going to show you how to do this for a 4-asset portfolio shortly. But when I did it for a 3-asset portfolio, the first thing I did is I just started creating random portfolios and then mapping them on here. And that's what all of these yellow dots represent. These yellow squares represent random portfolios that I created. Well, you could continue to do this for thousands and thousands of portfolio, and what you would eventually find is that there is a frontier, there's a line that bounds all of these portfolios. And that line starting right there, so that would be the minimum variance portfolio. That's the lowest standard deviation you could get by combining those various assets. Everything north of that on the boundary is considered the efficient frontier. So what is the efficient frontier? The efficient frontier tells you the highest return that you can possibly get by combining the assets in your portfolio for a given set of standard deviation. So at 15% standard deviation, that right there is the highest expected return we could get. So this red line represents what we call the efficient frontier. So any rational investor would prefer to be somewhere on the efficient frontier because the efficient frontier at all points is preferable to anything on the interior. But remember, what you could also do is combine this efficient frontier with a single riskless asset. So if you have the efficient frontier and you combine it with a riskless asset, then you could connect up the riskless asset with the efficient frontier. Now, you could shoot a line through any point, right? You could take the risk-free asset and you could connect it with any portfolio on the efficient frontier or inside the efficient frontier. But any rational investor would want to get the slope of this line as steep as possible because this becomes a real possible investment set. You could locate yourself somewhere on the line. Specifically, if you're anywhere between the riskless asset and the tangency point, that would mean you just have some combination of the risk-free asset and this risky portfolio right there on the efficient frontier. In order to get north of the efficient frontier, what you would have to do is short the risk-free asset, so borrow money at the risk-free rate, and then take the extra proceeds along with your equity and go long in that particular portfolio right there. So the key point, and this should all be reviewed from your 410 class, is when you have a bunch of risky assets, you can combine them into portfolios, but the best you can do with those portfolios is the efficient frontier. However, if you also introduce a riskless asset, you can jump from the efficient frontier onto what we call the capital allocation line. And just as the efficient frontier is preferable at all points to any interior portfolios, the capital allocation is likewise preferable to the efficient frontier at all points except for the point of tangency. But one of the real critical things to understand is the only way to get on the yellow line is you have to move on the efficient frontier to the point of tangency, create that portfolio, and then decide how much of that portfolio you will have relative to the risk-free asset. Now, a couple of notes here. So we call that portfolio the market portfolio, or the optimal risky portfolio. We could call it the optimal risky portfolio. So the capital allocation line depicts the linear risk-return relationship for the combination of this optimal risky portfolio and a risk-free asset. Like we said, it is at all points preferable to the efficient frontier except at the tangency point. This means that all investors should prefer to hold some combination of that optimal risky portfolio and the risk-free asset. Now the equation of this line can be defined thusly. Your expected return on your overall portfolio, which is going to be a combination of the optimal risky portfolio and a riskless asset, will be the risk-free rate, that's the y-intercept, plus the slope of the line times the standard deviation of the portfolio. So there's the standard deviation of the overall portfolio. How do we get the slope? Well, it's rise over run, which would be the expected return on this optimal risky portfolio minus the risk-free rate, there's the rise, and the run would simply be the standard deviation of this optimal risky portfolio, since the riskless asset has a 0 standard deviation. So I want to get right into it because I have a lot to show you in order for you to be able to execute this. So the deliverable is going to be everything you did last class. We're going to build on that. So we're going to take what you did last class and we're going to build an efficient frontier, and then we're going to map the capital allocation line. We're going to use the same data set that we used in the previous module. We're just going to build upon it. So if we come over to our output from the 10th Excel module, we learned how to use matrix algebra to figure out the expected return and standard deviation of a portfolio. We also learned how to optimize that portfolio. Now what we want to do today is map out the efficient frontier. So let's go ahead and create a tab. We'll just call it the efficient frontier. And we're going to put some input variables in here. The first thing we're going to put in is exactly how many portfolios do we want to analyze, and you'll see what I mean later. The next input that we're going to need is what's our maximum standard deviation multiplier, and you'll see what that is shortly. And we're also going to need a risk-free rate. So what we're going to do is we're going to start creating portfolios that we'll use to map the efficient frontier. We ultimately need to figure out the expected return and the standard deviation, but what we're going to need is we're going to need a target standard deviation, and we're also going to need an actual standard deviation, and you'll see what I'm talking about shortly. Now, in order to do this, what we're going to need is we're going to need portfolio weights. So we'll go ahead and put that here for each of our 7 assets in your case, but I'm only doing it for 4 assets. So if you remember, I have TLT, GLD, AGG, and SPY, and then I'm going to need a total portfolio weight, and then ultimately we're going to need to figure out the slope of the capital allocation line. That's going to be very, very important. So we're going to just make a whole bunch of portfolios, and that's going to help us map out the efficient frontier. Now why don't we start out with 20 portfolios, but we'll try to make it so that we could accordion this a little bit. So right here, I'll just do a simple equation. I'll say if this previous portfolio equals nothing, then give me nothing. Otherwise, if you take that previous portfolio and add 1, if that's greater than the number of portfolios that we've put as our input, then also give me nothing. Otherwise, let's go ahead and give me another portfolio. And we'll roll that out there a long ways, but it should stop at 20. Perfect. Now, in order to get the expected return, what we're going to do is, remember, we're going to take our weight vector, we're going to transpose it, and we're going to multiply it against the expected return vector on this other tab. So before we do that, why don't we put some weights in just to get us started. So let's just do equal weighting to get things going. And I'm just going to copy and paste that over as far as we want it. And that's just, like I said, that's just going to help us get things going. And let me make it so that we can see all these things on the screen at one time. That'll just help us out a little bit. Okay, so in our first portfolio, in order to get expected return, what we're going to do is matrix multiply. We're going to transpose these weights right here. And we're going to multiply that against our expected return vector, and we should lock that in so that we can drag this formula across. Anytime you're doing matrix multiplication, you have to hit Control, Shift, and Enter. Turn that into a percent, give it a few decimals, and you may want to even give it 3 decimals. All right, now, what we want to do is we want to map out the efficient frontier. In order to map out the efficient frontier, what we're going to do is we're going to list out several possible standard deviations, and we'll use Excel to figure out the highest possible return we could get for each of those standard deviations. So that's how we're going to map the efficient frontier. We'll go ahead and put in the possible standard deviations, and then we'll just ask the question, what's the highest expected return we could get for each of those possible standard deviations? Well, we know what the lowest standard deviation is that we can possibly get because we solved for that. So if you go back here, look, our minimum variance portfolio has a standard deviation of 99.2 basis points. So we'll just put that in. We also want to make it so that our last standard deviation is what we'll call our maximum standard deviation. Now, we could use, for instance, if you look at the individual assets comprising my portfolio, the highest standard deviation is 6.05. We could use that. But if we use that, you're not going to get a very good curve in your efficient frontier. It would be better if we could take it out a little bit farther just so it'll show us the efficient frontier a little more clearly. So this is where we're going to try to determine a little bit of a standard deviation multiplier. And I'm going to start with 2.5. What that means is my maximum standard deviation that I'm going to analyze is going to be 2.5 times my highest standard deviation for any of the individual assets. And I'm just going to do, this formula is going to seem a little bit involved, but it's not too bad. So what I'm going to say is if the year equals nothing, give me nothing. Otherwise, if the year equals this last year, then why don't you go ahead and give me 2.5 times my max individual standard deviation. So in order to do that, I'll just do max and I'll highlight all of the standard deviations. Okay. But if that's not true, then what we want to do is we want to take the previous standard deviation, which would be C7, and we want to add to it the difference between our max and our min, which, remember, our max is 2.5 times the max of all these individual standard deviations. So that's our max. Okay, subtract out our min, which we already have established over here in cell C7. So that's how far we have to travel. Now, how long do we have to get there? Well, what we're going to have is we're going to have the number of portfolios minus 1. And I'm always very nervous when I do a formula like this that just has a lot of parts to it that I may have made a mistake. And so let me just read through this real quickly. If the year equals nothing, give me nothing. If the year equals the last year, then give me my multiplier times my max standard deviation. If that's not true, then give me my previous standard deviation and add to it the difference between my max, which is my multiplier multiplied by my max on the previous page, minus the minimum that we've already established, divided by the number of years minus 1. That should work, but we need to lock a whole bunch of things in. Specifically, we need to lock in A1, A2, anything on the optimization tab. There's A2, there's the optimization tab, and A1 again. Hit the enter button. Turn this into a percent. Give it a few decimals, and we should do the same here. And drag this across and just see if it looks like it's working for us. And we'll know very shortly if it's working. So it's giving us a max standard deviation of 15.12, which should be 2.5 times this standard deviation right here, which it is. So it looks like we did that formula correctly, and you technically should be able to stretch that all the way out. Okay, so now in order to get the actual standard deviation, what we're going to do in order to get the actual standard deviation is we're going to take, remember, W transpose sigma W. So M molt, this is from the previous Excel module, transpose our weights, multiply that by the variance covariance matrix and make sure you lock that in, and then multiply that back against the weights, which are C10 through C13. Now remember, you have to take the square root of that in order to get standard deviation. So square root of all of that and Control Shift Enter. And format it a little bit here. And it's 2.52. Now you have a sanity check on this because earlier we did an equally weighted portfolio. It's right here. There's the equally weighted portfolio, and we got a standard deviation of 2.52, which is what we're getting right here, which is very good news for us. Now you could put these inside if-then statements if you wanted to. So you could say if this year equals nothing, give me nothing. Otherwise, give me the matrix multiplication. But don't forget Control Shift Enter. By doing that, you should be able to slide it all the way across, like so. And you should be able to do the same thing here. So you could say if the year, or the portfolio, I'm sorry, if the portfolio equals nothing, give me nothing. Otherwise, give me the square root. And again, Control Shift Enter. And you should be able to slide that all the way across. So the nice thing is, this will accordion for you. At least all of this part will accordion for you. This part down here you're going to have to do some hand manipulation with, but we're trying to make it as dynamic as we can. So what we can do then is we can actually start going through this, and we can saying, all right, here are all the standard deviations that we're going to use in order to map out the efficient frontier. That will represent the x-axis for our efficient frontier. What we need to do is figure out the weights that will give us the highest expected return for that given standard deviation. Down here, the total portfolio weights will just be the sum of all the weights, and we need that because it's going to be an important constraint for us. So we'll copy that all the way across. In fact, you could put that in an if-then statement if you wanted to. If the portfolio equals nothing, give me nothing. Otherwise, give me that. And you should be able to send that all the way across. Okay. Now, in order to get the capital allocation line slope, remember that the slope of the capital allocation line will be the return on the optimal risky portfolio, in other words, the efficient frontier portfolio, minus the risk-free rate over the sigma of the optimal or the efficient frontier portfolio. So what we'll want to do is we're going to want to take the expected return on this optimal risky portfolio on the efficient frontier. We'll subtract out the risk-free rate, and we'll divide it by the actual standard deviation of that portfolio. We'll lock in A3. And that doesn't give us too much information because we haven't put in the risk-free rate. Well, we'll do that at the very end. And also, you could put that inside the same if-then statement. So the nice thing is we're making this dynamic, except for the weights are the only things that you're going to have to mess with by hand. Okay, forgive me for just a second as I do a little bit of formatting. I'm going to step away. You don't have to watch the formatting. But I just want to get this looking as sharp as I possibly can. Now I want you to pick back up right here because I just wanted to show you one thing I'm doing that you might not figure out on your own, although I think I showed it to you a few modules ago. I want to black these in right here because there's no data there. This is kind of a breakpoint in my data table. So actually what I'm going to say is if that equals nothing, give me nothing. Otherwise, I want you to give me just black. And then I'm going to highlight all of that. I'm going to go to conditional formatting, format a new rule, only cells that contain a specific text, specifically the text black. And if it contains the text black, then I'm just going to fill it with black, just to make it pop a little bit. So, okay, I'm going to do the exact same thing down here. You don't have to watch that. Okay, so what we want to do at this point, and this becomes really, really important for us, is we want to actually start mapping out this efficient frontier. So for every potential standard deviation, we've got to max out the expected return and figure out the weights that will do that for us. Well, remember, here's the way to do it. You go to the Data tab, Solver, and what you would do is this. So for the first portfolio, what we would do is we would want to take the expected return and we'd want to max it out by changing these weights subject to two constraints. The first constraint is that the total portfolio weight has to equal 1. And the second constraint is that the actual standard deviation has to equal the target standard deviation. Click OK. Remember to uncheck the Make Unconstrained Variables non-negative. Solve it. And so you can see that this is the weights that are put forth, and we might want to give those a couple more decimals, or at least one more decimal for a little more precision. But you can see that it says if we want to get a target standard deviation of 0.99%, this is on a monthly basis, then the highest the expected return is that we can achieve is 0.415%. We'll see if that lines up with what we did earlier in Excel Module 10. In Excel Module 10, we calculated the minimum variance portfolio. That was the standard deviation, and in fact, we calculated the highest expected return was 0.415%. So, looks like we're on the right track. Now, what we want to do is we want to repeat that process for all of these portfolios. Now, I hope you can appreciate that's going to be a tedious process. You would literally have to repeat that 20 times. You have to go to the Data tab, get the solver, clear it out, so reset it all, and then you'd go back through it. I want to try to help you in this process. I hope that this doesn't overwhelm you, but I want to help you create a macro so that you can do this a little bit more quickly. Here's how we're going to do it. We're going to try to record the macro. So first off, go to put your cursor in the cell that you want to maximize. So we want to maximize cell D6. Go to the View tab, Macros, and we're going to record a macro. And we're going to call this the max return macro, and I'm going to give it a capital M as the shortcut. So if I hit Control-Shift-M, it will run this macro. Okay, it's now recording. I'm going to go to the Data, Solver, and I'm going to reset it, clear it out. What I'm going to do is I'm going to max out the return by changing the weights, subject to the constraint that the total overall portfolio weights have to add up to 1, and the actual standard deviation has to equal the target standard deviation. Uncheck the unconstrained variables non-negative box, click Solve, and there we have it. Okay, now stop recording. So go back to View, Macros, stop recording. Now that macro won't work, and let me show you why. So we're going to have to get into a little bit of VBA here. If you go and view that macro, so go to Max Return and click Edit. I just want to focus on the Max Return macro, and so it's down here. So concentrate your eyes down here. Please notice that this is what's happening with the actual code. We're resetting the solver, and then we're setting that first cell that we're going to maximize to D6, and we're telling it to maximize it by changing cells D10 through D13. Well, the problem is when you move over to this column, it's still going to go and do it for the D column, which is not what we want. We want it to do it for the E column. So instead of having these be fixed references, we need to make them relative references. And this is how we're going to do it. Every time you maximize a column, you put your cursor where you want to maximize. So you probably should make a note to yourself, a user note. That might be very helpful. So you might want to do a user note. In order to use max return macro, set cursor in cell to be maximized. Hotkey is Control-Shift-M. Okay, so what we're going to do is this. We're going to turn all of these fixed references into relative references by doing this. We're just going to say we want to maximize the active cell. Okay, and we don't want to do it by changing D10 through D13. We're going to use this offset function, and this is how it's going to work. We're going to say active cell, but we're going to offset it, and specifically we're going to move down a certain number of rows, and let me show you what I mean. If we put our cursor there and we go down 1, 2, 3, 4, that's where we want to start in terms of what we're going to change, and it's going to cover 4 rows. So how you do it is this. You offset it by 4 rows and 0 columns. So all that does is that tells it start in the active cell and move down 4 rows. Then we're going to say take the range that goes from A1 through A4 if you start 4 rows down. So this is a little cumbersome, but what it says is start in my active cell, go down 4 rows and stay in the same column, and take a range that basically just covers 4 different rows. So stay in that same column and cover 4 rows. Okay, we need to do the same thing down here. Now remember, what we want to say is we want to say that the total portfolio weights have to add up to 1. Total portfolio weights are going to be right here. So that's 1, 2, 3, 4, 5, 6, 7, 8. 8. We need to offset it by 8. So what we're going to do is active cell offset 8, 0. And that tells it go to that cell, and that has to equal 1. Down here, now we're going to have to say that the actual standard deviation has to equal the target standard deviation. So that would be an offset of 2 for the actual standard deviation and an offset of 1 for the target standard deviation. So right here, we're going to do active cell offset 2, 0, and it has to equal active cell offset 1, 0. Now that should be technically all that we need. So some of this was just some other clicking that was going on. We don't need that other clicking. We do need it to solve it, so you can see this little line right here, solve or solve. We absolutely need that. Now, one thing that you might not be aware of, and look, some of this other stuff is unnecessary, so we can delete the rest of it. One thing that you might not be aware of is after solve or solve, I want you to put in one more line of code. Put in user finish colon equals true. What that's going to do is it's going to make it so that that dialog box at the very end doesn't pop up. And right before the solve or solve, we're going to put in one other option. So you type in solver options assume non-neg colon equals false. Now you remember when we pulled up the solver dialog box, let me see if I can show you this. If you go to data solver, remember you need that box unchecked. That's all we're doing with that one line of code. So when we put in solver options assume non-negative colon equals false, that's just going to tell Excel uncheck that box. Alright, this macro should work. What we're telling it is reset the solver dialog, and then wherever our cursor is, we want to maximize that by changing the 4 cells. So what we're saying is we're going to change cells starting in 4 rows below where the cursor is and going 4 rows down. We're also going to give it some constraints. So the first constraint is take the active cell, go down 8 rows. That's the total portfolio weight, and that has to equal 1. We're also going to say if you go down 2 rows, so take the cell that's 2 rows down from the cursor, that has to equal the cell that's 1 row down from the cursor. So that's us simply saying that the actual standard deviation has to equal the target standard deviation. Now, pause. You're doing a portfolio of 7 assets. I'm doing a portfolio of 4 assets. This is going to change slightly. You're going to have to think for a second about how many rows down you need to go. This stuff won't change. But when I said go down 4 rows and then have it go 4 deeper right here, A1 through A4, you're going to have to go 3 more rows. So you'll have to do A1 through A7. Also, when we said that this has to equal 100%, well, that was 8 rows down from the cursor. 1, 2, 3, 4, 5, 6, 7, 8. But you're going to have 3 more assets. So you'll have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You'll have to go down. So again, there's going to be 3 more assets. So imagine those will all be assets, and your actual total portfolio weight will be right there. So you'll have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So your 8 is going to have to turn into an 11. And there might be some other changes, but I think that's it. So as you do this for yours, it's going to be slightly different than what I did. But that should work. And what's really handy about this is come back in. And by the way, I noticed that I made a mistake here. So I'm going to come back into this second column and I'm going to test it out. So here goes my first attempt at my macro. I put my cursor in the cell that I want to max out. I'm going to hit Control-Shift-M. And we're going to see if it actually maximizes it out and keeps the constraints the way that we want them. And you can see that in fact we have our portfolio weights equal to 100%. The actual standard deviation equals the target standard deviation. So now you can see that all you have to do is go across these 18 other portfolios and just hit Control-Shift-M and it will optimize it. You don't have to watch me do that, so I'm going to step away for a second while I do that. Okay, so now that I've done that, and by the way, it doesn't take very long as you don't have a lot of programs up and running. I had some other Excel files with macros open, which was bogging it down. But it really doesn't take long. If you just go across, hit Control-Shift-M, and it will maximize those for you very quickly. One other note I realized that I might need to show you. If your macro is not working, if you hit Control-Shift-M and it's not working, then you might need to go back in and view your macro. So go to Max Return, edit it. You may need to come up to Tools, References, and you might need to click on the solver function. If that's not enabled, then it won't work. So make sure that's checked. But it should work as long as that's checked. Okay, the next thing that we want to do is we want to actually start creating the capital allocation line. And in order to create the capital allocation line, what we want to do is map out this yellow line. So we just want to identify what would be the expected return for the yellow line for all of these different standard deviations. Okay, now I don't want anybody to get confused here. I'm going to do this in the exact same table, okay? But keep in mind that when we do the capital allocation line, we are moving on the efficient frontier to a single point, specifically the tangency point. So everything we do with the capital allocation line will be combining this one optimal risky portfolio with a risk-free asset. So it probably makes sense at this point to go and get the risk-free asset. So let's do what we've done in previous Excel assignments. We're going to go and get the risk-free asset. Let's go to the FRED add-in and let's go and get, now remember, I'm going to use a 20-year treasury note. Some people would tell you that you need to use T-bills. Some people use 10 years. But I'm going to use the 20-year because that's consistent with what Ibbotson does to get the equity risk premium. So I'm going to go ahead and get the FRED data here. We're going to change it into monthly data. It's going to pop up as daily data, so we'll change it monthly. And I'm also just going to go back 5 years. So what I'll do here for the beginning date range is I'll just do today minus 365.25 days times 5. We'll update the data, and we'll just go ahead and calculate the average, and we'll figure out the average monthly risk-free rate. So the average yield on the 20-year T-bond over this period has been 3.7%. Let's divide that by 100 since it's an integer, turn it into a percent, and let's divide that by 12 to get us our monthly equivalent. And so that's going to become our risk-free rate. So right there, let's go ahead and type that in. There's our risk-free rate right there. And let's make it so that we can see it. And again, turn it into a percent and give it as many decimals as we need. Okay, so now what we want to do is we want to figure out the expected return of the capital allocation line. And I should probably put that in here. Capital allocation line expected return, but this is where the one point where you might get lost and you might get confused. Remember, what we want to do is we want to figure the capital allocation line that gets us the farthest northwest on this graph that we can. Now, we can match up and create capital allocation lines that go through any realistic portfolio. So we could have a capital allocation line connected with that portfolio right there. But you can see that the slope of that particular capital allocation line wouldn't get us as far northwest as we could get. So when we figure the capital allocation line, we want the capital allocation line with the steepest slope. And wherever the steepest slope is for the capital allocation line, that's our optimal risky portfolio on the efficient frontier that we're going to combine with a risk-free asset. So what we have to do is we have to look for the maximum capital allocation line slope. And I don't care if you want to make it simple on yourself so that you actually remember, you could even do this. Okay, max CAL slope. And then you could say, all right, now what's my CAL expected returns? And if you wanted to do that, you could just do, all right, well, what's my max for all of these? right? And you could lock that in. And that's not necessary, but it's just going to help remind you that that's the capital allocation line that we're using. And you would have to put that inside of the if-then statement that we've used previously. So all that's saying is this. All right, for every single portfolio on the efficient frontier, so up here we've figured out the efficient frontier. Here's the possible standard deviations. For every single standard deviation, we combined these 4 portfolios to figure out the maximum expected return we could get. So this right here represents the efficient frontier. There's my x variable, there's my y variable, and we'll create a chart here in a second. So that was creating the white line. Maybe you want to see this to make it a little clearer. That was creating the red line, right? Highest expected return for a specific standard deviation. Now we want to match it up with the risk-free rate. And in order to do that, we're going to pick the portfolio on the efficient frontier for which the slope of the tangent line is the steepest. That portfolio happens to be somewhere in here. And we need to give it one more decimal point in order to actually see it. So we can see that the highest sloped capital allocation line would be the capital allocation line that meets up right here with this second portfolio. So that's going to be the portfolio of risky assets. That's the portfolio of these 4 assets that we're now going to match up with the risk-free rate. Now, how do we get the expected return then for all of these different standard deviations? So what I need everybody to understand is we're going to use the same x-axis. Same x-axis for the capital allocation line that we're using for the efficient frontier. But what we have to figure out is what will the expected return be? Well, in order to get the expected return for the capital allocation line, let's go back to our PowerPoints. And you can see that the expected return on our overall portfolio is the risk-free rate plus the slope of the capital allocation line times the standard deviation. So all we have to do is go and figure out for every standard deviation, multiply it by the slope and add the risk-free rate. So we come back here and please understand now what we're doing is for every possible standard deviation, we're going to figure out the highest expected return on the capital allocation line, which means we're going to multiply that standard deviation by the slope of the capital allocation line. Remember, not these slopes. We've now picked the highest slope, the tangent portfolio, and that's where we are. We're moving to the tangent portfolio, and that's all we're dealing with. So the slope will be constant, and it will be the highest slope possible. So for every point, we're going to take the standard deviation, multiply it by this highest slope possible, and add the risk-free rate. So we're just going to take standard deviation, times the max slope, and we're going to add on the risk-free rate, and that needs to be locked in. You could put that inside of the if-then statement. Give it a little bit of formatting help. All right, so what we have done is we have mapped out the efficient frontier up here. What does that mean? For every single possible standard deviation, we've figured out the highest return we can get by combining those 4, or in your case, 7 risky assets. Then what we did is we found which of the efficient frontier, so which of these possible portfolios on the efficient frontier, which of those, when combined with a risk-free asset, would give us the highest sloped capital allocation line. So we mapped out the efficient frontier, and then we just linked it up with a risk-free asset, and we looked for the highest slope. And it turned out that it was this portfolio right here. So then what we said is, okay, if we link that up with a risk-free asset, so just this portfolio, and we link it up with a risk-free asset with different weights, okay, and we're going to figure out the weights in a second, then what are all of the possible expected returns that we could get? And in order to do that, you simply take the slope of the capital allocation line times whatever the standard deviation is of the overall portfolio and add the risk-free rate. So we said, okay, for all these possible standard deviations, multiply it by the max CAL slope and add the risk-free rate, and we get this expected return. And what you need to see is these expected returns on the capital allocation line are all dominant to the efficient frontier. The expected return on the yellow line dominates the expected return on the efficient frontier, which means everybody should prefer to get on that yellow line. The last piece of the puzzle is this. We know that we're going to have some combination of the risk-free asset and this optimal risky portfolio, and this is the optimal risky portfolio. So we create a portfolio that consists of 99.7% AGG, 18.2% GLD, and is short 11.4% SPY and 6.5% TLT. We create that portfolio, and then we combine it with the risk-free asset, but what are the weights? So now let's figure out the weight of the risk-free asset and the weight of the optimal risky portfolio. The last piece of this puzzle is to figure out the weights, and this is not that hard. You just have to remember that where you have two assets and they each have a return, and we're going to create a portfolio that has weights, so we're going to put a certain amount of our portfolio in asset 1, and we'll put the rest of our portfolio in asset 2. So these, in our situation, would be the optimal risky, or sorry, the risk-free asset and the optimal risky portfolio, because remember what we're doing with the capital allocation line is combining our optimal risky portfolio with the risk-free asset. So these are our two assets. Then remember that the expected return on our overall portfolio would equal the weight in asset 1 times the return in asset 1 plus 1 minus the weight in asset 1 times the return in asset 2. Well, think about what we already know. We know the overall expected return. That's what we just calculated. We also know the return for asset 1. That's just our risk-free rate. And we also know the return for asset 2. That's what we calculated up here when we mapped out the efficient frontier. So specifically, the expected return on asset 2 is the expected return right here on our optimal risky portfolio. So we could do some algebra and we could solve this equation for W1, and what you'll find is that W1 equals the return on the overall portfolio minus the return on the second asset divided by the return on the first asset minus the return on the second asset. So that's how we're going to calculate the weights. So all we have to do is this. For every point in our capital allocation line, we're going to take that expected return and subtract out the expected return on our second asset, which is the expected return on our optimal risky portfolio, which is that second portfolio. And we divide it by the difference between the return on our first asset, the risk-free rate, and again, this optimal risky portfolio. What you'll see then as we start to map out the capital allocation line is there's the weight on our risky there's the weight on our risk-free asset. Then to get the weight on our second asset, we just take 1 minus that. Now remember, we're going to have to lock in some things. That D7 needs to be locked in because we're always using this optimal risky portfolio. So we need to lock that in, and we need to lock in A3 because that's our risk-free asset. Now we could put this inside the if-then statement. And we should be able to shoot that across. Give it a little bit of formatting TLC. And we also should be able to do the same thing down here. We'll just put it inside the if-then statement. So if the portfolio equals nothing, give me nothing. Otherwise, give me 1 minus the risk-free weight. And we send that across. And again, give it some formatting TLC. All right, so what is this saying then? What this is saying is we've created the efficient frontier. We connected the efficient frontier with the risk-free asset and found that the place where you have the steepest slope, so we connected the risk-free asset with all the points on the efficient frontier, and the place where we get the steepest slope between that line is the second portfolio. So that becomes our optimal risky portfolio, so that becomes our max CAL slope. Then what we did is we used this equation to figure out the expected return at all points on the capital allocation line by simply using that formula. So we figured out the expected return all along the capital allocation line. We made the observation that the expected returns on the capital allocation line dominate the equivalent expected returns on the efficient frontier, which is what we expected. And then we used this equation down here to simply figure out the weights at all of the different points. Now, we know that we did this right because right here at a standard deviation of 1.74, we got 100% weight in the optimal risky portfolio, which makes perfect sense because we're right here. Where we are is we're at the tangency point, and at the tangency point you would be 100% invested in the optimal risky portfolio. Once you go past it, now you have to short sell the risk-free asset and leverage into the optimal risky portfolio. We can now delete this and we can draw out or map the actual efficient frontier. So this is the last task that we need to do. So we're going to insert a scatter plot with lines, and what we want to do is we want to first off map out the efficient frontier. So we'll select the data and we'll go ahead and call this the efficient frontier. For the x-axis, we just want the target standard deviations, so we send that all the way across. And then for the y variable, we want the expected returns. We click OK, and we go and check out what we have. Okay, so we can see that I made a mistake, and the mistake is obviously in the standard deviation, and maybe you caught this earlier. I'm not going to go back and redo the video. I forgot when I did the standard deviation formula to lock in right here the C8, and let me tell you what that means. If you go through this equation right here in cell D8, it says if there's no portfolio, then don't give me a standard deviation. If the portfolio number is the last portfolio, then what it's saying is, so if the portfolio is the last portfolio, then give me my maximum individual standard deviation from the optimization spreadsheet times my multiplier. So in other words, if this is the last portfolio, give me the maximum standard deviation. But what if we're in between? If we're in between, then we slowly want to ratchet up. So what we want to do is we want to take the previous standard deviation and add to it. How much do we want to add to it? We want to add to it the difference between the max and the min divided by however many periods we have to get there. Well, I forgot to lock in the min is the problem. So once I lock that in and send that across, I think that's going to fix things for us. Right? So now things will look a little bit better, but now the unfortunate thing is I have to go back in and re-optimize all of these. So I'm going to have to do my Control-Shift-M real quickly all the way across, and you can see how quickly that's going now, so I actually don't mind having you watch it. And as we do this, you're going to see the efficient frontier start to take shape right before your eyes, which I think is kind of interesting. You might not find it quite so interesting. And the last thing we need to do is add in the capital allocation line. So select data, we're going to add the capital allocation line. We're going to use the exact same thing on the x-axis, but now the y-axis is going to be the expected return on the capital allocation line. Like so. We click OK and we come back over, and you can see, in fact, now it doesn't look quite as clear and pretty as what I showed you before, something like this, but you can in fact see that the capital allocation line is dominant and preferred to the efficient frontier. Now you could make this bigger so that it's a little bit more visible and easy to see. You could even send it to its own tab, and I might recommend that just for visibility's sake. So send it to a new sheet and you get it looking like this. So with 4 assets, the blue line represents the efficient frontier and the red line represents the capital allocation line. Okay, so what's the point of all of this? The point of all of this is, if you believe in modern portfolio theory, then what you should do is you should go and get a bunch of assets and create the efficient frontier. Modern portfolio theory says we all prefer to be in the northwest on this graph. We want the highest level of return for whatever risk we can create. So when you combine all those assets together, you're going to create this efficient frontier. Once you've created the efficient frontier, go and find a risk-free asset and link it up with the efficient frontier. So you'll link it up with all the points on the efficient frontier. Since we want to be northwest on the quadrant, you should pick the line that has the steepest slope when you connect the risk-free asset with the efficient frontier. That's the capital allocation line. The way you get on the capital allocation line is by forming the optimal risky portfolio. So that's the point where you get the steepest slope on the capital allocation line. Form that optimal risky portfolio, and then combine that with the risk-free asset such that you locate yourself on the capital allocation line at the level of risk with which you are comfortable. So in our particular case, you've created the efficient frontier, you've mapped out the capital allocation line, and all you do is say, how much monthly risk can I tolerate? And now please note, you could make a lot more portfolios and make this a lot more precise, but maybe you say, man, the most I can stomach is 2.48% of standard deviation per month, which is actually quite a bit. If you arrived at that conclusion, then what you would say is, all right, I want to short the risk-free asset 42.85% and go long 142% in the optimal risky portfolio, which is the portfolio that's comprised of those 4 assets weighted the way that you see it highlighted there. So what you would do is, if you had $10,000, what you would do is you would short the risk-free asset to the tune of $4,285, and you would invest $14,285 in this optimal risky portfolio. I hope that the video makes it clear for you. If it's not clear at all, please come see me or the TAs. Best of luck in mapping out the efficient frontier and the capital allocation line, which would allow you to locate yourself on that line, which would tell you exactly how much weight to put in the risk-free asset and how much weight to put in the optimal risky portfolio, and precisely what the weights in the optimal risky portfolio would be. Best of luck.